Hello, my name is JAlfieri. I am in EC 311, 331, and 341. Today, I'll be talking about a power system in a cell phone. This power management system consists of two parts, a rectifier and an RC circuit. We will be focusing first on the rectifier. You want to consider if it is linear and time invariant. So first, to figure out if a rectifier is a linear system, you have to figure out if it passes the properties of homogeneity and additivity. What you do, you graph the signal and see if you add another signal to it, if you get the same outcome for the output. The system is nonlinear. You will, however, find that it is time invariant. I could go in and run a test on the rectifier today, or I could run one 2 days from now. I would still get the same result. We can consider the diode bridge as almost an absolute value mathematical function. It takes an input and only produces the magnitude of that input. So if you have a negative input to that component, you only show the positive magnitude of it. We'll consider the electronics part of a rectifier. And all a rectifier is composed of 4 diodes. And these diodes have a PN junction, where the materials inside the diode are doped with different chemical compounds. These chemical compounds create a bias in the side of the junctions when a voltage is applied across it. Basically, you have a positive and a negative side because of a diffusion current, where positive charges want to flow over to the negative charges, while the negative charges want to flow over to the positive charges. At the same time, you have something called drift current, which tries to oppose this change. And since you have this depletion region that forms of positive and negative ions, you have an electric field that occurs. This electric field causes a potential within the diode, and the only way that a current can flow through that is if it overcomes this potential. We like to call this VD on. Usually it's a typical value of about 0.8 volts. If you have a voltage, an input voltage that is lower than this, the diode would not conduct. No current will flow through it. It's as if the diode acts as an open in the circuit. When you apply a potential on the P-type or P side of the PN junction, also known as the anode, this is called forward bias. And this potential helps with the drift current and decreases that depletion region. Let's consider the electricity and magnetism component of figuring out what the electric field actually is. So when you go about it, you have a region of positive ions and negative ions. To figure out the electric field of this, you want to find over the area, you have to use a Gaussian surface. This Gaussian surface uses the technique of Gauss's law, where the surface surrounds a charge distribution. In this case, we have a planar symmetry of charge distribution, so we want to use a planar Gaussian surface. This Gaussian surface will uncover much of the charge, but not all of it. You will find out that the E field outside of the Gaussian surface is 0, because the flux going into it subtracts the flux going out to it. So only charge inside of the Gaussian surface produces an electric field. You'll find that when you're taking the electric field over the negative ions, that you have a negative electric field because of negative charge. When you go to the positive side of the region with positive ions, you'll find that the electric field increases to a positive value because of positive charge. If you want to find the voltage, you have to integrate over this whole area, and since the electric field is a constantly changing negative slope and then a constantly changing positive slope, you'll see a quadratic for the voltage. Now let's consider the other part of that power management system. Remember, we had the rectifier, and now we have the RC part. You can consider this the load of the full wave rectifier. So first we want to figure out if this part of this circuit is linear. So you first have to solve the linear properties of homogeneity and additivity. Solving for the differential equations, you figure out that this part of the circuit is indeed linear. It passes additivity and homogeneity. And another way you can figure out if it's time invariant is if the outside parts of each part of the differential equation, which you find are constants. If they're constants, this means it's time invariant. It does not have to do with time. If you consider if the diodes from the full wave rectifier are of different voltages, the output voltage over the load actually be of the RC circuit. By applying Kirchhoff's voltage law, and you find that a smaller voltage drop over the diode equals the largest voltage drop over the output. And because of this, you can also consider the power of the RC circuit, where if you have a smaller voltage over the diode, you will have a larger power dissipation over. Another thing you want to consider is why do we use a capacitor? Why can't we just use an inductor, for example? And the reason for this is the capacitor is having a change in charge over time when you apply voltage on it. And to be able to do this, you want to find the current through it. And you need something that acts as an integrator. The capacitor acts exactly as is. And if you integrate, you can find that the current through the capacitor is C dV dt, where the change in voltage is instantaneous when you apply to it. So once you apply voltage over it, you find it's infinite. Hence, it acts as a short at t equals 0. On the opposite end, in a steady state, there's no current flow through it because there's a physical separation between the parts of the capacitor. If you graph V out in terms of V in from the rectifier, that you will slowly get a steady state voltage, basically a DC, hence why it's called a AC to DC voltage. One last thing to consider is the reason you would want to find, hey, why is it time invariant or linear for an LTE system is if you're able to find those, you can find the convolution. Convolution basically shows you the output of any circuit. Hey, what's the output of this or this before even building it? Spending your time, spending your money on this. It's very useful. Thank you very much.